All right, here we go. We are on 3-2. This is part 2. We've got like 3 concepts today. Are we ready for that? 3 things. 3 things. Number 1 is something called the empirical rule. This is like concept number 1 for the day. Number 1, empirical rule. Here's what the empirical rule says.
A question. Would you be opposed to walking with Billy so that he is taller than you?
I don't care.
But you still play the games.
All right.
So Ellie and I walk together.
Just so that you have someone that is taller than you.
And he wants to drive the fastest.
He wants to drive the basketball.
I don't know what's going on. All
Yeah,
right.
But you'll
Okay.
still play the games with him.
Here we go. Empirical rule, this bell curve, you're going to want to come back to it and reference it. I will give you an additional sheet of paper that's laminated that has a bell curve that looks like this here, like in a couple days. Okay?
We have one though. This.
Oh, yeah. Yeah. You have a big one. There you go. You've got a big one. And it's got stuff on the backside. Okay, I'll give you one of those laminated. Yep. You've got a big one of these in your notes, okay? So here is what the empirical rule said. Some old dead guy came up with this. He looked at data set after data set after data set, like thousands of numbers, whatever. And here's what he said. He said that if you have a data set that is normally distributed, where like the most people are in the middle, and then you like let's say height. Most people are in the middle, and then you have very, very few tall people over here and very, very few short people over here. Okay? It's not skewed data. It's not data that looks like this. Okay? Or data that looks like this, right? It is normally distributed data. Okay? If you have normally distributed data and you have your average that lives here in the middle, this is your mean. If you add the standard deviation one time and subtract the standard deviation one time, 68% of your data will live in that region, right? So let's say my mean is 80 and my standard deviation is 5. I can conclude, if this is a test or something, that approximately 68% of my students scored between a 75 and an 85, right? Then if I add and subtract it again, if I subtract one more and add one more, that gives me a 90 and a 70, and I can conclude that 95% of my people scored between a 70 and a 90. If I add it and subtract it one more time, that's 95 and 65, and I can conclude that 99.7% of my people scored between a 65 and a 95. Okay? On average, when you calculate your standard deviation, you can add and subtract it this many times and all that stuff. Now, they also have it broken down chunk by chunk, so I can say that what percent of people scored between an 85 and a 90? 13.59, right? They have them like broken out like that. Now, does everybody score from -3 to +3? Standard deviations. This is -3 standard deviations. This is +3 standard deviations. No, 99.7%. That means that 0.3%, like less than 0.5%, 0.3% lives outside of that. Or in other words, 0.15, they say 0.15 or 0.15 lives on the outside of them. Right? Now, if you are in that 0.15, you are in like the tail ends, right? Okay, so that's how that works. Yep. But everything underneath of here is 100%. Those all add up to be 100%. Got it? Not too bad? Okay, let's do an example. Here we go. IQ scores have a bell-shaped distribution with a mean of 100. That's kind of fancy. Here we go. Here's your bell curve. Draw it as best you can. Mine still are not very good. 100 lives here in the middle. Okay? With a standard deviation of 15. Let's do some symbols. What symbol do we use to represent 100? The mean. Do you remember what he was called? X bar. Yep. And then 15 is your standard deviation, yeah? Okay? And we call that S. All right? X bar and S. If we add 15 and subtract 15, that goes to 115 and it goes to 85, yeah? That's one standard deviation. Whoop. 68% lives there. All right? If I add and subtract it again, that makes 130 and, 70. If I add and subtract. And in that region, 95% lives in that region. And if I go again, and I add 15 and I subtract 15, this is 145, and this is, 55. And 99.7% of people are going to be in that range. Got it? Yeah? All right, now here's what they're saying. They say what percent live between 70 and 130? 70 is here, 130 is here. What percent is that? 95%.
So can't you just like do this and then like look?
But yeah, you just look under your bell curve thing. Yep, exactly. Yep, makes sense? Yeah? What if they would say, hold up, what if they would say what percent lives between like 85 and 130? 68 plus whatever this is, right? Okay?
13.5.
Okay, because this is like -1 and this is like +2. Do you know what I mean by that? This is subtracting 1 standard deviation and adding 2 standard deviations. So I'm going -1, which is here, and +2, which is here. So I'm adding these 3 chunks together, right? Or basically 68 plus this chunk. Yeah? Does that make sense? Do we see how that works? Okay? So that is the empirical rule. Got it? Yeah? Okay, now, a different dead guy with the last name of, this is called, try to pronounce that. How do you pronounce that?
Wait, say that again, Reese.
I said it the wrong way.
There's no L.
How do you pronounce it?
Chebyshev.
Chebyshev. Chebyshev's theorem.
Chevy said.
Chebyshev's theorem. That is his last name, okay? And he said something different. Here's what he says. It says the proportion of any set living within k standard deviations. So like 1 standard deviation or 2 standard deviations or 3 standard deviations, right? From the mean is always at least 1. I'll write this down over here. 1 minus 1 over k squared. That's the percent that lives within that many standard deviations, but only for numbers greater than 1. Okay? So for example, let's say I want to go 2 standard deviations, right? Here's where x bar lives. Okay? Here is -1, here is +1, here is +2, here is -2, -3, +3, right? Instead of doing the whole bell curve thing like they do, right? He came up with different percentages. So they both agree that it's like a bell-shaped curve, but they came up with different percentages. And here's what they say. If I'm going -2 plus 2, I'm going to plug 2 in for k, right? And 1 over 2 squared. This is like 1/4, right? So I've got 1 minus 1/4. What is 1 minus 1/4?
Like
3/4. 3/4 is what percent? 75%. So they conclude that 75% lives within 2 standard deviations, right? Okay, 3 standard deviations would be 1 minus 1/3 squared. 1/3 squared is 1/9, right? So 1 minus 1/9 is 8/9, and 8/9 as a percentage or as a decimal is 0.8 repeating, so 0.888 or 88.9%, right? Lives within 3 standard deviations. Does that make sense? Okay. Why can't you do 1 standard deviation?
0.
Yeah, 1 minus 1 over 1 squared is like 0, so that doesn't work. So they can't figure this one out using Chebyshev's. This one is not as widely used for that reason, right? Because 1 standard deviation we don't have a rule for, right? But they're saying that that number like increases that way, okay? The number of standard deviations, 1 minus 1 over k, that's the formula that they use. 1 minus 1 over k squared, okay?
Are they going to ask us to? Okay.
All right, IQ scores have a mean of 100 and a standard deviation of 15.
The same thing we just
Whoop. 100 here, standard deviation of 15, so we're going 85 to 115. We're going 70 to 130. We're going 55 to 145, right? Okay, what can we conclude from Chebyshev's theorem? What percent lives within 1 standard deviation?
0.
Whoa, sorry. What percent lives within 2 standard deviations?
70.
75% fall within 85 to 115. No, wrong. 70 to 130, right? We're doing 2 standard deviations. Okay? What percent fall within the next one?
88.9.
88.9 or 89? 88.9 fall within 55 to 145 region. Does that make sense? Okay? The discrepancy is between the percentages because they're not quite consistent percentages. What percent did the empirical rule say was within 2 standard deviations?
96.
95. They say 95% rather than 75%. What do they say about 3 standard deviations? 99.7% as opposed to 88.9%, right? So there's just a little discrepancy on percentages there. Okay?
Top number of IQ. Like, what's your highest?
I don't know. That's a good question.
Have you ever taken it?
No, I never have actually.
Taken what?
An IQ test. I don't know what the highest IQ
We should.
is. Yeah, I think you can take all sorts of different kinds of ones.
Like,
But-
below 70 is like.
Yeah, probably. Is like, yeah, so below here. I don't know. It's not good. I don't know.
Mentally challenged and then like a bonus. Like mentally gifted or whatever.
Yeah, right. Yeah. So I don't know. Anyway, so the difference between empirical rule and Chebyshev's, they're both telling you the same thing, but there's a discrepancy on percentages. We will use, going forward, we will use this guy all the time. We use the empirical rule. A lot. Lots of people use the empirical rule. Okay, last, that was concept number 2. Do you need me?
Oh,
We're gonna go down to the FCS.
Oh, sure. Okay, that sounds good. The last concept, number 3, right? I told you 3 main concepts. This is number 3. And this is something called the coefficient of variation. Okay. The coefficient of variation. All right, here we go. Let's say we're talking about, I'm going to use an example over here. Let's say we're talking about SAT scores and ACT scores, right? Okay, ACT scores, you guys know a little bit more about the ACT, right? It goes 0 to 36, 36 being the highest, right? Okay, let's say the average ACT score is a 21? No, it's way smaller. It's way less than that. It's like, we'll go 19. We'll go 19, right? Okay, average ACT score is a 19 with a standard deviation of 3, 2, 3, 2. Okay, standard deviation of 2. All right. SATs, I mean, know about the SAT? I think it goes like 0 to like a bunch.
1600.
1600 is the highest?
Yeah.
Okay, so what do you think the average is? Let's just guesstimate.
1,000.
What?
Oh, I bet it's like 950. Probably.
We'll go 950 is the average with a standard deviation of how much?
200.
200?
I want to do
Let's go 200. We'll go 200. It's fine. Okay? With a standard deviation of that. Okay, now, I am taking both tests, right? And on this test, let's just call me X. I'll call, yep. My value is X. And my value, I scored an 1100. Okay? Slightly above average, right? On this one, I scored a 21. Did I do better on the SAT score or did I do a better on the ACT score?
Let's find out.
Better on the ACT.
Oh, yeah.
Yeah, because you're with it. No. Yeah.
Yeah.
Because you're farther that way.
The range is smaller.
that's
You
one.
think so?
That's one standard deviation.
That's
Oh, yeah.
less
And
than
that's
it.
ACT,
That's less than it.
That's more than.
And this is more than one standard deviation, right? So here, and that's something called a z-score, which we'll get to, okay? So like my z-score here would be above 1, right? Here my z-score would be exactly 1, right? So which one did I do better on?
ACT.
No, wait. The SAT, the score, z-score was less than 1, true? If I add 1 standard deviation to 950, that would be 1150. So I did less than 1 above, right? Okay? Here I did exactly 1. So did I do better on ACT or SAT? I did better on ACT, okay? So the reason why some of this stuff exists is so that I can compare apples to oranges. Like I want to be able to compare SAT and ACT, but I can't because they're not on the same scale, right? Okay? So there's something called the coefficient of variation, and it allows you to relate standard deviations and averages, okay? So here's 2 things that we're comparing. We are comparing Verizon data speeds and we're comparing earthquakes. Data speeds and earthquakes, and I want to know which one has more variation. Okay, which one is more consistent and which one has more variation, right? It would be quite interesting if we could say that Verizon data speeds have like less consistency than earthquakes. True? Like more variation. Okay, so that's what we're comparing. We're comparing data speeds and we're comparing earthquakes.
So that's like some crazy statistics when they're like comparing
Right, exactly. Yeah. I'm like, okay, I know how much that is in miles, but what is that in kilometers? It's kind of like that type of thing. Like putting it into relative terms, right? Okay. So data speeds, it gives me that there were 50 Verizon data speeds. Here's what I'm going to call that. We don't actually, yeah, we do use that. No, we don't. Hold on just a second. Hello. Yes.
Yeah, I know. I was like, that's your.
You do? Gosh, dang it. She just got off of an antibiotic for it. Poop. Okay.
Are you okay?
Okay.
Like,
Give me just a second and I'll come down there. Okay. All right. Bye. I don't have time for this. Okay. Malia's ear hurts and she's got a temperature. Okay. All right. Let's go. Data speeds. There are 50 Verizon data speeds. That means that N is 50. That's what we call it. N is the number of numbers that we have. All right. Magnitudes of 600 earthquakes. That means N for earthquakes is 600. All right. For Verizon data speed, the X bar or the average data speed is 17.60. With a standard deviation of 1602. For earthquakes, the average is 2.572 with a standard deviation of 0.651. Here's what I'm trying to figure out. I'm trying to figure out which one is more consistent numbers. Like this standard deviation is very much small, right? But the numbers are smaller, right? So does this one have more variation or does this one have more variation, right? Like I get that this has a really small standard deviation, but its numbers are smaller. And this one has a larger standard deviation, but its numbers are larger, right? So which one has more variation? Which one's range is more spread apart, right? Okay, so here's what we're doing. We're doing a coefficient of variation. Here's how we do it. We take the standard deviation and divide by the average. Standard deviation is 16.02, where the average is 17.60. 16.02 divided by 17.60 is something. It's 0.9 something probably.
and you're dividing them?
Yes. 16.02 divided by 17.6. And I get 0.91-ish. Okay?
Times 100.
Then they say take it times 100, but all that's doing is that's changing it to a percent. So this has a 91% variation. 91% variation versus this one. If I take 0.651 and I divide by 2.572, I get something. 0.651 divided by 2.572 is 0.253. We'll go 0.253,
25.
which has 25.3% variation, right? So here's what this means, folks. This is saying that data speeds for Verizon have more variation than earthquakes do, i.e., or in other words, Verizon data speeds are more inconsistent than earthquakes. True? Doesn't that sound stupid? Verizon data speeds are more inconsistent than earthquakes.
That's because earthquakes are always the same.
Yeah, right? Like most earthquakes are like smaller, right? Whatever. Okay? But when you say it out loud, it's kind of like, well, yeah, Verizon sucks, right? Like so that's what people are thinking in their heads, right? Like,
No, I
oh,
was just thinking like
Verizon's
usually
terrible, right?
earthquakes
They are more inconsistent than what earthquakes are, right? So this one has more variation. Okay, so kind of like when we're comparing apples to orange on SAT and ACT, I want to be able to compare and see which one has more range or which one has more variation. Verizon data speeds has more variation. Got it? Let's see what the question asked. Bloop. Note that we want to compare variation among data speeds to variation among earthquakes. This one has more variation. Got it? Questions about that? Yes.
Why did we write down N?
What?
Why did we write down
We didn't need N. We didn't need N. But I'm just training you because, like, going forward, we'll be doing lots of examples where N will be a factor in there. So just get used to writing everything down in terms of N's and S's and all that stuff. Okay, one more thing, because I know they're going to ask it on your homework assignment. Let's talk variables. Let's talk the difference between N and N. Let's talk the difference between S and sigma. Let's talk don't go there. Don't go there. Let's talk the difference between X bar and mu. Don't go there. Don't go there. This, I've never had to before, like, say those words. Don't go there. But evidently I do for this class. Whatever. Mewing. Mewing. I don't know. Whatever. Okay, here's the deal. Ready? Oh, wait. Let's talk the difference between S and sigma squared.
Wow.
Sorry, I'm adding that in there. You can add in below if you want to.
Squared?
Yep. Oh, S squared and sigma squared. Sorry.
Does that mean you're like the alpha?
No.
On the
Wherever you want to. In a corner. Wherever you can fit it.
Can I have a
Okay? What does N mean? Lowercase n. The number of numbers. Number in the sample. What's capital N mean?
Number in the population.
The number in a population.
Hold on.
Okay? So when they use those variables, that's what that means. Lowercase n is the number in the sample. Uppercase n is the number in a population. Okay? S, little s, is the standard deviation for a sample. Okay, we haven't talked about this before. Sigma is the standard deviation for
Population?
a population. Yeah. Those ones are a little bit different variables, but you'll get used to seeing those. What is S squared? That's the variance. Do you remember how we talked about, like, variance is the square of the standard deviation variance
So is that in a
for
population?
a sample? Okay, this is variance for a population. Okay, what's X bar?
Hold on.
The mean or the average for a sample. Okay, this guy, have we talked about mu before?
micrometer.
Mu is called mu. M-U. That's how it's like pronounced. Mu, right? It looks kind of like an M and a U at the same time, so that's how I can remember it. Mu. He is the mean for a population. All right, we'll do more variables than just those 8, but that'll be going forward. These are ones that you should remember. Okay? Because I think they ask you a question on it on your homework assignment. Okay? Beautiful. There you go. Okay? Those main concepts. Got it? We are done with 3-2. So have 3-2 homework all the way done for tomorrow. We'll start on 3-3. Okay, goodbye.
Can I use the restroom?